In this video, we are going to discuss about glucose and lactose biosensors. So, by the end of this topic, the students can be able to understand the fundamental multi-layer structure of electrochemical biosensor, and they can able to analyze the enzymatic reaction of glucose oxides and lactose oxidase. So first we go through biosensor. So biosensor is an analytical device that combines the biological element with the transducer for detecting the specific chemical substance. When we look at the functional block diagram on the slide, the process begins when a target analyte interacts with the bioreceptor, which can be an enzyme or antibody or nucleic acid. So this interaction produces a highly specific biochemical reaction, and the transducer immediately captures this biological event and converts into a measurable physical signal such as electrical energy or voltage. Finally, the signal conditioning circuit will amplify and process this raw data, displays in a clear quantified readout form. And here the attention specifying to the glucose biosensor is glucose monitoring is the most widespread and commercially successful application of a biosensor technology. Actually, this is used in the clinical management where patients must track their blood sugar levels multiple times a day to avoid the acute or chronic complications. So the development of these things will have the highly accurate systems, and this can be transformed diabetic care from complex laboratory procedures to simple painless self-monitoring at home itself. So here the operational chemistry of a standard glucose biosensor is actually glucose oxidase, which we are commonly call it as GOX. So this enzyme is actually catalyze the oxidation of the beta glucose into gluconic acid, that is glucose plus oxygen gives gluconic acid plus H2O2, that is hydrogen peroxide. And to convert this chemical reaction into electrical signal, we use the amorphoric transduction. In an amorphoric biosensor, you can see the voltage is applied between the electrode and the reference electrode. So the hydrogen peroxide byproduct will diffuses the working electrode, which undergoes electrochemical oxidation, and this reaction will liberates the electrons to generate a small electrical current. Also, because of the magnitude of this current, it is directly proportional to this rate of hydrogen peroxide production, and it is producing highly linear precision measure for the original glucose conversions. And early glucose monitors known as first generation biosensors, they are creating the major technological challenges like oxygen limitations, where variations will be causing in the blood oxygen levels. So to solve this only, we use the second generation biosensors. So this replaces the oxygen level with chemical molecules that we call it as electron mediators. And next is the enzymatic architectures of the lactase. So here the operational design of this one is it is chemically analogous with the glucose sensor, and also it is using the lactase oxidase. And when it comes to the multi-layer membrane design and the activities, there are we can see the actual assembly, that is that it ensures the biomedical sensors where it remains more highly selective with the complex biological systems like whole blood. So this will be used in the multi-layer membrane for over the electrode, and the outer layer of this membrane will control the influx of the molecules, and finally this structure molecules will be collected from the specified layer which acts as the chemical shield, and this passes through the blocking range. Finally, it reaches the data will be collected in the acquisition systems. So in the first generation, You can see the first generation of the biosensors will be given to the based on the hydrogen peroxide, and finally based on this technology we are finally expanding to the glucose oxidase for replacing the dissolved oxygen. Thank you.